Hello everyone, in the previous lesson, we derived the first n terms of the arithmetic sequence and two forms of the formula. Can you describe the method for deriving the first n terms and formulas of an arithmetic sequence and accurately write these to formulas? We started with the Gaussian head-to-tail pairing method, went through the process of classification discussion, and finally discovered the method of reverse order summation. Formula 1 has been derived. Then we use the general term formula of arithmetic sequences to represent the sum of the top n terms in the set using the first term and tolerance, and obtain formula 2. In this lesson, we will continue to apply the first n terms and formulas of arithmetic sequences to solve some comprehensive problems. A school has built a new auditorium and requires it to accommodate 800 seats. The auditorium has a total of 20 rows of seats. Starting from the second row, the back row has 2 more seats than the front row. How many seats should be arranged in the first row? This is a practical problem. Can you explain the general steps of using mathematical methods to solve practical problems? Firstly, we need to transform practical problems into mathematical problems. Find the solution to a mathematical problem. Restore the solution to the actual problem. So let's first transform practical problems into mathematical problems. We notice that starting from the second row, the back row has 2 more seats than the front row. If we set, if there are n seats in the nth row, then this sentence can be expressed as n minus and n minus 1 equals 2, where n is greater than or equal to 2 and n is a positive integer. According to the definition of arithmetic sequence, n is an arithmetic sequence with a tolerance of 2. The lecture hall has a total of 20 rows of seats, which refers to the number of items in the sequence, where n equals 20. It can accommodate 800 seats, which means S20 equals 800. How many seats should be arranged in the first row is the requirement for the first item A1 to be equal to. So, the actual problem is transformed into such an arithmetic sequence problem. How should we solve this problem? The 4 quantities involved in the problem exactly match the sum formula 2 of the arithmetic sequence. Knowing 3 numbers, find 1 number, and solve the equation. When writing the answer process, everyone should first explain the process of problem transformation and the meaning of symbols clearly. The seats in the lecture hall are arranged in a column from row 1 to row 20, forming a sequence n. The sum of the first n terms is sen. According to the meaning of the question, the sequence n is an arithmetic sequence with a tolerance of 2, and S20 is equal to 800. According to formula 2 for the sum of the first n terms of the arithmetic sequence, it can be obtained. S20 is equal to 20 times the first term A1, plus 20 times 20 minus 1 divided by 2 times the tolerance d equals 800. Solving the equation yields A1 equal to 21. Finally, we will restore the solution of the mathematical problem to the solution of the actual problem. That is to say, 21 seats should be arranged in the first row. I hope everyone can seriously appreciate the ideas and methods of mathematical modeling. Let's take another look at a mathematical problem. Given that the sum of the first n terms of the arithmetic sequence n is sen, if A1 is equal to 10 and the tolerance d is -2, does sen have a maximum value? If it exists, find the maximum value of sen and the value of n when obtaining the maximum value. If it does not exist, please explain the reason. Many students may feel a bit at a loss when they see this question, so let's write down the sequence to make the problem more intuitive. The first term A1 of the sequence is equal to 10, and the tolerance d is -2. Therefore, a 2 is equal to a 1 minus 2 equals 8, a 3 is equal to a 2 minus 2 equals 6, a 4 is equal to a 3 minus 2 equals 4, and so on. Next, we will calculate sen. S1 equals A1 equals 10. S2 is the sum of the first 2 terms, which is 10 plus 8 equals 18. S3 is the sum of the first 3 terms, and we can add the sum of the first 2 terms S2 to the third term A3, resulting in 18 plus 6 equals 24. S4 equals S3 plus A4 equals 24 plus 4 equals 28, and so on. We see that the transition from S to S4 is increasing. Why does it increase? You should have noticed that starting from S2, when we calculate each Sn, we add a n to the Sn minus 1. Since a 2 to a 4 are all positive numbers, so every Sn we calculate is equal to Sn minus 1 plus a positive number, which is naturally larger than Sn minus 1. Will sen continue to increase? No, because the tolerance d is a sequence less than 0, and a n is a decreasing sequence. When a n decreases to no more than 0, sen no longer increases. What does this mean that the sum of items is the maximum value of Sn? The sum of all positive terms is the maximum value of Sn. Which items are positive numbers? We can use the general term formula to solve it. Clarify the problem-solving approach. Let's solve it specifically. Firstly, we will explain that the sequence n is a decreasing sequence according to its definition. From a tolerance equal to -2, we can conclude that n plus 1 minus n equals -2, which is less than 0. This indicates that adding 1 to n is less than n. This indicates that from the second term onwards, each term of the sequence n is smaller than its preceding term, making the sequence n a decreasing sequence. Next, we will examine the positive and negative values of each term using the general term formula. From a equals 10 and d equals -2, it can be concluded that n is equal to the first term 10 plus n minus 1 times the tolerance of -2. Thus, it is equal to -2n plus 12. We make n greater than 0, resulting in n being less than 6. This indicates that when n is less than 6, n is greater than 0, when n is equal to 6, n is equal to 0, and when n is greater than 6, n is less than 0. That is to say, from a 2 to a 5 are all positive numbers, and a 6 is 0. Starting from a 7, they are all negative numbers. So S1 to S5 is increasing, S6 and S5 are equal, and then decreasing. So when n is equal to 5 or 6, Sen is at its maximum. We substitute the first term and tolerance into Formula 2 for the sum of the first n terms in the arithmetic sequence, and then we can calculate that S5 is equal to 30. So the maximum value of Sn is 30. In fact, when n is greater than or equal to 2, since n is equal to Sn minus 1, n is the amount of change from Sn minus 1 to Sn. The sign of n reflects the clear increase or decrease of Sn, and the maximum or minimum value is found. Since the key to finding the maximum or minimum value is to analyze the increase or decrease of Sn, do you have any other methods to study the increase or decrease of Sn? We often use the perspective of functions to examine the increase or decrease of variables. To study the variation of Sen with increasing number of terms n, Sn can be regarded as a function of n and the monotonicity of the function can be examined. Solution 2, where a 1 equals 10 and d equals -2. Sn is equal to n times a 1 plus n times n minus 1 divided by 2 times the tolerance minus 2, organized as -n plus 11n. This equation has the form of a quadratic function with respect to n, and we can use the graph and properties of the quadratic function to study it. We will obtain the complete square of -n minus 11 seconds in its formula, plus 121 divided by 4. It can be seen that the corresponding quadratic function opens downwards, with the axis of symmetry n equal to 11 seconds. Since n is a positive integer, the maximum Sn occurs when n takes the integer closest to 11 second, which is 5 or 6. We substitute 5 or 6. The maximum value that can be calculated from the sum of -n squared and 11n is 30. The monotonicity of functions is a commonly used method for studying maximum or minimum values. In this question, Sn has the form of a quadratic function with respect to n. So for a general arithmetic sequence, do the first n terms and formulas have the form of quadratic functions with respect to n? We further organize the first n terms of the arithmetic sequence and Formula 2, and arrange them in descending order according to the number of terms n. Sn is equal to the square of half d times n plus a 1 minus half d times n. For ease of expression, we will simplify this formula as Formula 3. Can you answer question for now? Please pay attention. The quadratic coefficient contains the parameter d, and only when d is not equal to 0, Sn has the form of a quadratic function with respect to n. What other characteristics can you observe from Formula 3? You may observe many characteristics, such as the constant term being 0 from the structure of the equation. Even some students may find that it must have a structure of a n square with bn, where ab is a constant. From the value of the coefficient, the double of the coefficient of the quadratic term is equal to the tolerance d. The sum of the coefficients of the quadratic term and the first-order term is equal to the first term, and so on. We solved an example problem in the last class where we know that the arithmetic sequence n satisfies that the sum of the first 10 terms is 310 and the sum of the first 20 terms is 1220. Let's find the expression for the sum of the first n terms. In the last class, we solved this problem using the method of fundamental quantities. Do you have any new ideas when you see him again in this class? From the previous analysis, it can be seen that the first n terms of the arithmetic sequence in sen have the form of a n square plus bn. As long as the values of real numbers a and b are determined, the expression for sen can be obtained. Two independent equations are required to solve the two unknowns a, b, and exactly two conditions are given in the problem. We substitute n equals to 10 and n equals to 20 into the expression for sen, respectively, to obtain a system of binary linear equations about the real number a, b. Solving this system of equations yields a equal to 3 and b equal to 1. Thus, sen is equal to 3n squared plus n. The first n terms of the arithmetic sequence in sen have the form of a n squared plus bn. So conversely, and more generally, if the first n terms of the sequence a n in sen are equal to a n squared plus bn plus c, where abc is a constant, what are the properties of this sequence? Let's take a set of values and observe the pattern. To improve efficiency, we use Excel for calculations. In a spreadsheet, we can substitute the given values of a, b, c into the first n terms and the formula sen equals a n squared plus bn plus c, calculate the value of each sen, and then calculate each term of the sequence by a 1 equals s1, a 2 equals s2 minus s1, a 3 equals s3 minus s2, and so on. Let's first take s1, b as 2, and c as 0. Calculate s1 to s6 and a 1 to a 6 for observation, where a 1 equals 3. Starting from the second term, each term is 2 larger than the previous term, and we assume that the sequence a n is an arithmetic sequence with a first term of 3 and a tolerance of 2. Let's try taking a few more sets of data to see if the sequence a n is still an arithmetic sequence. For example, we take s1, b as 2, and c as 1. Calculate that a 2 is 1 greater than a 1, and starting from a 3, each term is 2 greater than the previous term. This shows that the sequence a n is not an arithmetic sequence, but we speculate that it is an arithmetic sequence starting from the second term. Take a equal to 1, b equal to 0, and c equal to 2. At this point, the sequence a n also starts from the second term and is an arithmetic sequence. Let a b equal to 0, b is equal to 2, equal to 1. At this moment, the sequence a n is a constant sequence starting from the second term, and of course, it is also an arithmetic sequence. In the cases we have provided, the sequence a n is an arithmetic sequence starting from the second term, but it may not necessarily be an arithmetic sequence starting from the first term. Observing the given data, we can observe that in the case where the sequence a n is an arithmetic sequence, c is equal to 0. So, is it true that as long as c equals a 0 sequence, a n is an arithmetic sequence? Let's take a few more sets of data to try. A equals 2, b equals 1, and c equals 0. The sequence a n is an arithmetic sequence with a first term of 3 and a tolerance of 4. When a is -1, b is 1, and c is 0. The sequence a n is an arithmetic sequence with a first term of 0 and a tolerance of -2. When a is equal to 2, b is -1, and c is 0, the sequence a n is an arithmetic sequence with a first term of 1 and a tolerance of 4. Based on the above experimental data, what kind of conjecture would you come up with? Everyone may come up with such a conjecture. If the first n terms of sequence a n and sen are equal to a n plus bn plus c, then when c equals 0 sequence a n is an arithmetic sequence. When c is not equal to 0, the subsequent terms of the sequence a n from the second term form an arithmetic sequence. Can you prove whether this conjecture is correct? To prove this conjecture, one must be able to determine whether the sequence a n is an arithmetic sequence. How to determine if a sequence is an arithmetic sequence? We need to see if it meets the definition of an arithmetic sequence, which means that adding 1 to any positive integer n minus a n equals a constant t. To do this, we need to find a n plus 1 and a n. This requires finding the general formula for the sequence a n single quotes ... Do you remember the method of finding the general term formula through the first n terms and the formula? The first step, when n is equal to 1, a 1 is equal to s1. In the second step, when n is greater than or equal to 2, a n is equal to sen minus 1. In the third step, the conclusion is drawn based on the above. Next we will follow these steps to find the general formula for the sequence a n. When n is equal to 1, a 1 is equal to S1, which is equal to a plus B plus C. When n is greater than or equal to 2, a n is equal to Sn minus 1, which is the sum of a and b. This formula gives us the general term formula for the sequence a n. Next, we will examine whether this sequence satisfies the definition of an arithmetic sequence. Since the general formula is segmented, we first consider when n is greater than or equal to 2. At this point, both n and n plus 1 are greater than or equal to 2. A n plus 1 is equal to 2n plus 1 times a plus b, and a n is equal to 2n minus 1 times a plus b. Subtracting the 2 yields 2a, which is a constant. Because n is greater than or equal to 2, this indicates that the subsequent terms of the sequence a n from the second term onwards form an arithmetic sequence. Next, we only need to examine whether the difference between a 2 and a 1, when n is equal to 1, is equal to 2a. If they are equal, then the sequence a n is an arithmetic sequence. If they are not equal, then the sequence a n is an arithmetic sequence. The sequence a n is not an arithmetic sequence. After substitution calculation, a 2 minus a 1 equals 2a minus c. Obviously, when c equals 0, 2a minus c equals 2a. The sequence a n is an arithmetic sequence. When c is not equal to 0, subtracting c from 2a is not equal to 2a. The sequence a n is not an arithmetic sequence, but the subsequent terms starting from the second term can form an arithmetic sequence. Thus, we have proven the correctness of the conjecture and gained a deeper understanding and comprehension of the form and properties of the first n terms and formulas in arithmetic sequences. In this lesson, we applied the knowledge of sequence to solve the practical problem of designing seats for the lecture hall and experienced the practical value of sequence. Then, we explored the issue of the maximum value of the sum of the first n terms in an arithmetic sequence using two methods. One method is relatively microscopic, starting from the formula for the common terms of arithmetic sequences to study the impact of each term on the first n terms and changes in the sequence. Another method is relatively macroscopic, starting from the first n terms and formulas of the arithmetic sequence, treating the first n terms and as a function of the number of terms n, and using function graphs and properties for research. In this process, we arranged Formula 2 in descending order of the number of terms n, and obtained Formula 3 in the form of a quadratic function with respect to n and a constant term of 0 when d is not equal to 0. The general term formula and the sum formula of the preceding terms of an arithmetic sequence can both be regarded as functions of the number of terms n. Using the properties of functions to study the properties of sequences reflects the idea of functions. That's all for today's class. Goodbye, everyone.